Dr. L. Jones Tarsius Das, Professor of Mathematics, College of Engineering Gindi, Anna University, Chennai. He has obtained BSc and MSc Mathematics from Madurai Kamaraj University and PhD from Indian Institute of Technology, Bombay. He has served as NBHM Postdoctoral Fellow at Indian Institute of Technology, Bombay, and then as visiting faculty at University of Tennessee, Knoxville, USA, and Colorado School of Mines, Golden, USA. He is currently working as a professor in the Department of Mathematics at Anna University, Chennai. His research area includes numerical analysis of ordinary differential equations and partial differential equations. He has published more than 25 research papers in reputed international journals. He has visited many countries like USA, UK, Italy, Malaysia to participate in international conferences. He has completed DST SCRB funding project.
Welcome to UGC lecture series on computational mathematics, a laboratory practical course for BSc Electronics Honors students. Second lecture, we are going to see solution to system of linear equations. Basically, we are going to see the numerical methods for solving matrix equations. We are going to consider only n by n squared system. Particularly, we are going to see iterative methods for system of linear equations. In a broader sense, system of linear equations numerically can be solved, and these numerical methods are classified into two groups. One is direct methods, another one is iterative methods. In direct methods, we get exact solution within finite number of steps. In iterative methods, we refine every time approximate solution, and which will be near to the exact solutions. Particularly two methods we are going to see. One is Gauss-Jacobi method and another one is Gauss-Seidel methods. Both are iterative procedures, so it will never end. So we can stop the iterative procedures by assigning a maximum number of iterations or by computing the error between two consecutive iterates and make them to be less than a tolerance value. Since these two methods are iterative methods, we need a starting point, that is the initial approximation vector. So that we denote by x naught, and we solve algebraically each variable xi and we refine it iteratively to get exact solutions. And again, this is a iterative procedure, we repeat it for each variable so that we will go near to the exact solutions. At each iteration, we update the solution vector by using the system Ax equal to b. Here A is the matrix, x is the solution vector, and b is the right hand side given vector. In this problem, the given data are A and the right hand side vector b. So in this, during the iterative procedure, the matrix is not changed. Okay. Consider this system of n linear equation in n variable, and the given data are the matrix A11, A12, A1n, that is the first row, and A21, A22, A2n the second row, and similarly the last row AN1, N2, Nn, and the right hand side B1, B2 are also given data, and the problem is to compute x1, x2, xn the solution vector related with the linear set of n linear equations, and they are coupled one. Numerical method requires a starting point x naught. The idea of a Jacobi iteration is solving ith equation for ith variable. For example, consider the first equation, solve for the first variable x1. So x1 at the first iteration, subscript it indicates the variable, ith variable, superscript indicates the iteration, For the first variable, knowing the zeroth initial vector, we compute the first iteration by solving the first equation. Basically, the first equation we keep only x1 at the left hand side, all remaining values will be taken to the right hand side. So, you have this equation, and please note that right hand side are known value. We use the initial guess or initial value of the second variable, third variable, and so on nth variable, and the right hand side element b1, and the first row elements a11, a12, a1n. We solve the first variable iteratively. Similarly, the second equation is used for computing the numerical solution of second variable, and we keep only that term, all remaining term will be taken to the right side, and we get the second equation. In similarly, for the last variable, nth variable, we keep that variable at the left hand side, we take remaining to the other side, and using the initial guess, we get the first iterate for the first variable x1, second variable x2, and the nth variable. So, this is the first iteration for the system. In general, keeping all the variable at the right hand side at the previous iteration k, and we compute the k plus 1th iteration. Basically, consider the ith equation. I have given the method for the ith variable. Look at the left hand side, it is the ith variable at k plus 1th iterate is given. It is in term of take all the remaining values to the right side, bi is the known right hand side vector, and all the variable from j equal 1 to I minus 1 and j equal to I plus 1 to n except the ith variable, all other variables are taken to the right side, and we utilize the previous iterate k, and this is the precisely the Jacobi method. As a numerical example, we now see a 4 by 4 system. You have equation 1, 2, 3, 4 equations, and x1, x2, x3, x4, 4 variables, and all are related linearly. So, it is a system of 4 equations in 4 variables, 4 unknowns, and the matrix system is given here, and the right hand side vector is given here. And now we will see the numerical methods, basically the Jacobi iterative schemes. As I mentioned in the previous slide, the k plus 1th ith variable, first equation is solved for first variable, second equation is solved for second variable, and so on. The third and fourth variables are solved respectively from the third and fourth equations. And here I would like to make a point that the theory says that the numerical iterative procedure will converge to the exact solution for any initial iterate if the system is diagonally dominant. What I mean by diagonally dominant? The diagonal element in the absolute sense, in the modulus, should dominate the sum of other elements in the same row in absolute sense. For example, modulus 10, that dominates the sum of modulus minus 1 plus modulus 2. Similarly, it happens for all the other remaining 4 rows. So, the diagonal element in absolute sense should dominate the sum of other elements in the absolute sense on the same row, and that should happen for all the rows. Then only it is called a diagonally dominate. If the system is diagonally dominate, then the iterative procedure converges to exact solutions. So, that is theoretically it is proved. So, we verify that the given system is diagonally dominate. Suppose in some situation if the system is not diagonally dominate, try to rearrange the system equation with the right hand side term also, so that you will get a diagonally dominant. So, as I mentioned, the Jacobi iterative scheme, ith variable is solved for ith equation, ith variable is solved using the ith equation. So, first variable is solved using first equation, second variable is solved using second equation, and so on third and fourth. Basically we keep the ith variable from the ith equation, take all the other terms to the right hand side, and just refine, use the notation k indicates the iteration, use previous values and update the latest values. And by that, for example, when k equal to 0 in the previous case, I compute the first iterate, and this is the precisely the first iterate, and the initial guess it's 0 0 0 it's taken. You can choose initial vector as 0 0 0 or 1 1 1. The theory says that the convergence happens for any initial choice. For a suitable choice you can get a faster convergence, but for any choice definitely the scheme will converge. By substituting x naught, the previous 0th iterate as 0 0, I get the first value, and now first will be used in the right hand side, I will get the second iterate. Here you can see the tabular column, x1 0th iterates, it is the initial guess given 0 0 0, and first iterate value is given here, and the second up to 10 iterations are presented in the tabular form, you can see that. And the pseudocode, basically I am going to present the algorithm. Pseudocode is nothing but the method, the algorithm. We do not use any syntax or variable or processed on any programming language. It based on that the students can write a code and implement in the computer. From the system of equation you can build A and B. Building A and B are the data structure. Here A is a matrix, it is a n by n array, and B is the right hand side single array, and now initial guess is presented here, that we need it to start the iteration. Okay, compute, do certain block of iterations starting with the initial guess. Now here the k plus 1th iteration for ith variable is given, j equal to 1 to n, except the ith variable you have summation a I j x j k, that is subtracted from the right hand side ith variable, and the whole value is divided by a I. This is the iterative procedure which we see just now. And now what we are doing is we are computing the error. Since we get a solution vector at the k plus 1th iterate, and that is written in the form of x, and x hat that indicates the previous iterate, you will have components. Compare the corresponding components of the k plus 1th iterate and the previous iterate kth iterate, compare the corresponding ith component, take the difference in the absolute sense, and divide by the right hand side in the maximum. So that is the error. When the error is less than the tolerance value, you have to stop. So here we use do while computation. So the execution will be carried out till this error is greater than tolerance. Once the error is greater less than tolerance, the computation, the control will be exited out of the loop and the program will stop. The tolerance can be anything, it can be 10 power minus 6 or 10 power minus 10 or 10 power minus 15, 20. According to your own convenient decimal places, you can define a tolerance value and you can perform the computation. And this is the actual algorithm. The agenda of the prime aim of the method is to solve Ax equal to b and given initial guess. Okay. The input is number of equation and number of unknowns, and the entries matrix Aij for I equal to 1 to n and j equal to 1 to n, and the another input is the right hand side entries bi for I equal to 1 to n. How many equations are there? That many right hand side, and the initial the entries xo, xo indicates x old, and for that I is varying from 1 to n, and x capital O indicates the initial vector, you can have a tolerance value as say 10 power minus 5, minus 10 or minus 20, whatever you need it. And suppose if the tolerance is not achieved, the error is not less than tolerance, you can also stop the iteration procedure by fixing maximum number of iteration, that is given as n. Okay. And output is the approximate solution of the matrix equation. It is a solution vector x1, x2, xn. Okay. Then the set k equal to 1 iteration. Here this k stands for the iteration, starting from first iteration to maximum number of iteration. While this happens, then you perform this operation. This is basically the Jacobi iterative procedure, computing the latest iteration for the ith variable, and now compute the difference between the old iteration and the present iteration. It will be a component, each component will be compared, taken the absolute sense and maximum of it. So, if it is less than tolerant, then go for the next iteration. Similarly, you compute. So, at the end you just print out the latest iteration xi. We need to preserve the previous iterate, which will be stored in the variable xo, and that should happen for all the component. Okay. Now, we are going to see the next iterative method called Gauss-Seidel iterative procedure. Gauss-Seidel method is a just modification of the previous method Gauss-Jacobi iterative scheme. The thing is that while solving first variable, there is no change, it is same as the Gauss-Jacobi iterative procedure. When you solve for the second variable, we have the latest information of the first variable. So, why do not we utilize that? So, that is the modification of that, and it is an accelerated version of Gauss-Jacobi, and theoretically it is proved that Gauss-Seidel converges faster than Gauss-Jacobi, and most of the scientists they use Gauss-Seidel method. While solving, look at the solving the second equation, x1 is available. So, we use the previous iterate for that, for the latest iterate, current iterate for that. So, that is the basically the Gauss-Seidel. In the second equation, the latest information of x1 is available, we utilize that. In the third equation, the latest information of first and second variable, that information is available, we will utilize it. As in the end last equation, we have the latest information of all the remaining variables, we will utilize it. So, this is called the Gauss-Seidel method, accelerated modified version of Gauss-Jacobi. So, by that there is no change in the iterated solution for first variable. For second variable, note that we utilize the latest information, the first x1, this x1 is plugged here. Similarly, for the last variable, the latest information of all remaining previous variables are available. This is called the Gauss-Seidel method. And in the general formula, it's look at here, when we compute the latest iterate value k plus 1 iterate for the ith variable, we utilize the latest information of all previous variable. Look here, j equal to 1 to I minus 1 previous variable, and of course we have only the old iterated value for the remaining variable from I plus 1 to n. So, this is exactly similar to the Gauss-Jacobi, except this particular term we utilize the k plus 1th recent iterated value for the all previous variables. That is why it is called a modified and accelerated version of the Jacobi scheme. You can see that the change in that scheme. And for the same matrix 4 by 4, we just modify, look at here, for the first variable there is no change, for the second variable we use the latest iterated value, and for the third equation we have the latest information for x1 and x2 we use here. For the last variable we have all the latest information of first three variables we utilize here, and now the iteration is performed with the same initial guess 0 0 0, and you can see that what we obtained in the 10th iteration of Gauss-Jacobi, that is obtained here in the fifth iteration. So, theoretically it is proved that Gauss-Seidel method converges twice faster than the Gauss-Jacobi, and this is the same pseudocode, and of course you need matrix A and B, and you need an initial guess for starting the procedure, and the latest information of ith variable is computed using latest information of previous variable 1 to I minus 1 and the old information of a remaining variable I plus 1 to n, and the error is calculated as usual. Here small xi stands for the ith variable information of the current iteration, and xi hat there is a variable that is the ith variable information of the previous iteration. We need to store that also, and we take the difference in absolute sense, and we take the maximum value divided by the maximum of the right hand side, and that error you have to perform these computation till the error becomes less than or equal to the tolerant value. Otherwise, if it is greater than the tolerant value, you have to these computations will be performed. Once it is less than that, the control will be exited out of that program and the program will halt. Once again the pseudocode for that, you need A matrix, the right hand side B and the initial guess, and the number of equation is n, number of unknowns n, and the matrix entries Aij and right hand side Bi, and of course xo the old iterate value of the ith variable, and xo stands for the initial one. So, now the procedure starts. K equal to 1 first iteration, then k less than or equal to 1 perform step 3, 4, 5, 6, and this is a Gauss-Seidel iterative procedure, and immediately you compare the difference between the current iterate and old iterate, that is the previous iterate. Each every variable will be calculated in the absolute sense and maximum is calculated. If that is less than tolerance, go for the next one. So, continue this procedure and store the current one in this variable. So, we need to store just the previous iteration, and while computing the current we will compare with that, and once the conditions are satisfied the computation will halt. Either you have to go for maximum number of iterations or the error between two consecutive iteration is less than a tolerant value. In that case you can stop the procedure. Now we will compare that the Gauss-Seidel iteration method converges faster than the Jacobi method, and there are some cases where Jacobi iteration does not converge, but Gauss-Seidel both. And to accelerate Gauss-Seidel method there is another higher method. Students can refer that and write the code accordingly. That method is called successive over relaxation method. An additional example, a 3 by 3 case, and this is the matrix involved in that, the solution vector and right hand side vector, and can you see that this matrix is diagonally dominant. Look at the first row, the diagonal element is 4 and the sum of other element in the absolute sense, that is mod minus 1 plus mod 1, which is 2. The diagonal element dominates the sum of other elements in the absolute sense. Similarly for the second row and the third row. So, this system is diagonally dominant. So, you just ensure that whether your given system is diagonally dominant, or if it is not the case, then interchange rows so that you can get a diagonally dominant system. Even otherwise, if you do not get, perform the iteration. Sometimes it may converge or sometimes it may not. Diagonal dominance is a necessary condition. An initial vector is 0 0 is taken, and look at the first equation is solved for first variable, second equation is solved for second variable, third equation is solved for third variable, and this is the scheme for the first iteration, and this is the value you obtain, and the error with a this is the called the residual. In case of exact solution, b minus ax will coincide and that error will be 0. Since it is a 0th iteration, A000 only we have taken all variables as value 0. So, the difference between b minus ax naught, that will be a vector. B is a vector, ax bar is a vector, the difference is a vector. Then you take the equal the distance between the 0 and that vector. So, that value is the error, the residual value is 26, and for the first iteration the residual value is reduced to 10. Now, second iteration is performed. Now, the residual value is reduced to residual is what? The right hand side minus ax at the kth iteration, that gives the error, the residual value. Now, it is reduced, and for the third iteration the residual value is still further reduced. Actually, it should be 3, ax3, and the matrix is diagonally dominant. Jacobi methods iterations are converging. Similarly, now another example you see where the matrix is not diagonally dominant. In this kind of situation, sometimes the method may converge for a particular choice of initial iterate, sometimes it may not converge. In general, we cannot guarantee the convergence, only for diagonal dominance we can guarantee the convergence, and we choose the initial iterate 0 0, and we compute the first iteration, and the residual is 26.73 as in the done in the previous case. But look at the residual, the error, the difference between right hand side vector and ax bar vector in the taken in the distance between b is a vector, ax bar is a vector, the difference is a vector. We calculate the norm, the basically the distance, the magnitude of the vector. So, that increases for each iteration, you can very well observe that. So, diagonally dominance will guarantee the convergence, and similarly for the Gauss-Seidel case with the diagonal dominance, this is the residual error at the 0th iteration. Residual error considerably it is reduced compared to the Jacobi, it is faster convergence. So, you can see the error is reduced faster, and at the time the Jacobi iteration the error was 10, but here it is 3 point something, and the second iterate is computed, the error is reduced to 0.4. Compare with the same thing for the Jacobi iteration, the error at the second iteration is 6.7413, in Gauss-Seidel method the error is 0.4765. So, when both converge, Gauss-Seidel converges faster than Jacobi. So, now we will come to the summary. In this lecture we discussed two iterative procedure for solving matrix equations, Gauss-Jacobi method and Gauss-Seidel methods, and algorithms and pseudocode also we discussed in this lecture. I request the students to write the code for both the methods in any programming language, either C or MATLAB, and carry out different case studies, and also with diagonally dominant system with a different initial guesses, and a matrix with not a diagonally dominant system with a different initial guesses. Compute that and also compute the error and compare both Gauss-Jacobi and Gauss-Seidel method. Questions? Write actual programs for these two methods, Jacobi and Seidel. Students may use our pseudocodes for writing the actual program. You may use C language or MATLAB for doing that. Second, perform different case studies with different initial vectors. And third, do computations for both diagonally dominant and not diagonally dominant matrices. compute the residual error for each iterations. Exactly, you use our pseudocode. Pseudocodes are just a method algorithm without following any syntax or data structure, but students are asked to convert that into a programming language based on any programming languages like C or MATLAB, and perform several case studies for different matrix systems with the different initial vectors, and for both diagonally dominant and not diagonally dominant systems, and bring it out as a report. Thanks to the students for patiently listening to this lecture, and we meet again in the next lecture.